with the bare wall.
If we should follow the British tradition and associate titles, then of course the first succession, Michał Horodecki, would be Prince of Wales. Polish version would be Prince of Sopot, and Prince of Rzeszów.
Thank you very much. I'd like to thank you very much for invitation, and I hope to learn something. So I expect you'll criticize a lot this, and yeah. So I will tell about thermodynamics, but recast in some way that we borrowed from entanglement theory. And the work I present is rather basic, so you can ask after like so many years what basic is still to be done in thermodynamics. So for 100 years people try to derive heat bath, try to obtain probabilities from somewhere. But this I will not touch. It's not about this. I do not aim to solve this super ambitious problem. The other thing is that thermodynamics is not very good if we have microscopic system. So there is a question whether standard notions such as free energy, war, can be related to a small microscopic system. And so this is what we address here. To what extent we can have second law for microscopic systems. As well, we would like to get something that is model independent, some model independent limitations for processing microsystem with being in contact with a heat bath. So normally, if we normally people consider some couplings, some particular interactions, and prove something. We would like to be as much model independent as possible. We would like to have some ultimate limitations of what we can do with the microsystem. And we are interested in some limitations like amount of work that we can draw from a system out of equilibrium, which is coupled to a heat bath. To give a flavor what could be model independent results, let me present this one. If we have a system which is a heat bath, so it's in a Gibbs state, then if we apply arbitrary unitary, then the average energy can only go up. So this means, so here it's very general, yes, whatever unitary, however we will control the molecules, we cannot simply get the energy out of the heat bath, we can only put on average the energy to the heat bath. So this is very model independent. We assume this, but otherwise we do not assume anything about what we can do with this heat bath.
Why do you call the rock beta heat bath?
Yeah.
Well, it's a subsystem. It's a subsystem, and the heat bath is hidden there only in this parameter beta.
Yes.
So what have you has with beta?
So I assume that I have a large system which is in a thermal state, and how it happened, I don't care. So for the purpose of
the heat bath, I'm just.
Yeah, so for the purpose of this talk, I will call heat bath such a thing, a large system and a Gibbs state.
You will call the system heat bath?
If you like. But then a system will be yet another thing. So in this talk, the system will be some microscopic system that I will be coupled with it. Thank you. Maybe my terminology is wrong.
It's not an orthodox way.
Yes.
Yeah, exactly. Saying that you cannot get if you can switch back one slide.
Yes.
This expression means that the energy of a system
after unitary transformation is larger, but not the heat pump, not in changes with the heat pump.
Okay, I mean, this is some mathematical expression. Yes, but I think I should think about that terminology and maybe talk to you later, because it's...
The idea of the heat bath is that it is actually a closed system which is not trading energy with something else, because then there will be another heat bath.
Yeah, and another heat
Yes,
pump.
so if we take this cool derivation, I have a large closed system, then I take part of it, a subsystem, and this subsystem is which I will be interacting with. So I have my system which will be interacting with this subsystem of this big system. Yes, let it be. Yeah. Yes. Yes. Definitely. So. So as I said, average energy cannot decrease. Now one can ask, how about the distribution of energy changes? So, you know, with some chance you can get a little bit of work, even a large amount of work from the heat pump, but it will happen with small probability. Energy, meaning with some probability, the energy of the heat pump will go down, and then my system will go up. But it will happen. So people ask this question, and later. So it's related to fluctuation theorems. Fluctuation theorems tell us about the distribution of energy changes and roughly confirm that it can be, with very small probability, it may happen that some fluctuations where we will gain and normally we lose. So there are other questions. And now I introduce additional system, which is out of equilibrium. So I have this, what I called heat bath, and then I have additional system out of equilibrium. What we can say about this? So now we not only operate on a heat bath, but also on this system. So now clearly we can gain something, because the system may, it's out of equilibrium, so it's some resource. It's now we can, we may also, since this subsystem will be microscopic.
But is this additional system interacting with this heat bath?
I allow to switch on and off the interaction I want. So I assume it's like a working body where I can stick it to the heat bath and.
I know what I'm going to ask you.
Yeah.
So if we will discuss this way, this is rather complicated.
Yeah, but no, you asked me whether.
I hope you agree that it's usually helpful to allow this.
Go to the point.
The point is this additional third system interacting with the heat bath only, or
No, only with this subsystem, which is in a Gibbs state.
So how is this interacting via the additional new operation?
That's the thing.
By what?
I want to I would like not to assume anything about this interaction. I would like to get ultimate limitations that can come from.
That permits that the energy of this additional system will decrease.
Yes. So, and because it's microscopic, then it's natural to ask about some deterministic. So normally work is something that is some average. It's a macroscopic quantity. But since we have this system, we will be microscopic. Then we can ask, try to define something which is deterministic work. So it's not an average of some small changes of energy that add up to some average value, and but we may ask, we want to exactly this amount of work.
But
so
not all work is change of energy.
Yeah, exactly. Yeah, I will present here a paradigm where. Yeah, exactly.
I mean, it's a science where the precision of the definition is of some importance.
Yes, I will come up to precise definitions.
We don't say
Yeah, exactly. Exactly. It's very vague. What I say is extremely vague. Now I will give exact definition with which I hope you will disagree, and it will be nice. So what if we care about, and so that's the thing, we will try to come up with some notion of deterministic work, and also we would like to care about the form of the output state. So we'll be also interested, we have some system and we'll try to change it into its state. And the question is what we can do, what can be final form of the state of our system. So let's first, so regarding this first question about the distribution, as I said, it simply was developed in the form of fluctuation theorems. And yeah, the nicest, the most elegant to me is the Crookes form, which somehow constrains the distribution of work if we do arbitrary transformation of a heat bath. But I will not discuss this. Yeah, of energy changes. Now, now I will come up to this. So suppose we have to these two questions, and there is some work where Robert Talisky in '79 considered microscopic system which interacted with a heat bath, and he presented some Carnot engines with this microscopic system, but he considered some weak coupling with a heat bath. So the system was microscopic, but we would like not to be model independent, and also work was there an average quantity. So still we also want to, here we want to have deterministic work. Right, so what questions you can, so that's the situation, we have heat bath, some system, and then after we will switch on some interaction and we'll get some system in the output state, and of course some heat bath which will not be very interested in. So the questions you can ask are, what state-to-state transition is possible? And you would like to have non-trivial Hamiltonian of the system. If the Hamiltonian is trivial, then some things are known because it's related to Landauer principle, where this was some bit. So we want to have some non-trivial Hamiltonian.
What do you mean by trivial?
A trivial means like all energies are equal to the same. So like zero, like Hamiltonian is zero, because it's up to a constant. Yeah. So let's and the last question, it seems it was not addressed so far, this deterministic work. But if I am wrong, tell me. So as I said, we want to determine state-to-state transition, and we also want to do that not in a statistical regime, but just single shot, meaning only single copy of a system is available. And we want to develop this deterministic work. And finally, we want to ask to what extent the transition that we will consider here can be made without microscopic control of a heat bath. So now here are the tools that we, or the ideas that we took from entanglement theory. So there, we consider transitions from state to state via a given class of operations. So there it was two distant labs, and the class of operations typically was that one can send classical communication and locally can apply any operations. And then this restricted your transition. You cannot do anything with this class of operations. And it was interesting to study what state you can obtain from some initial state. So you would like ultimately to decide when you can go from one state to some other state. And we now, so that's a resource theory, because any state that was entangled was a resource. The states that are not entangled can be prepared for free by this class of operations. So you have some resource that is free and public, and there is some resource that is valuable. You cannot create it, you can only manipulate it. So here we will recast thermodynamics in this way. So let me introduce the class of operations. So in thermodynamics, energy matters, so our operations will be such that they will come up from interaction that preserves energy. So this is heat bath system, and we allow any interaction which so that now it will not put some Hamiltonian of interaction, but we will assume that we can will look only at the very result of the possible interaction, and the result will be some unitary that acts on the whole system. And because we want to account for energy, we it should commute with the total Hamiltonian, but without interaction term, because whole interaction will be here in this unitary. Okay.
This is not the total energy of the system.
This is the energy of a system when they are far apart. then we should imagine that it's like we have some. It's more like collision theory. So we have the working body is far apart from a heat bath. We now put it into contact, and then and we take it away. And finally, you have something like S matrix, yes, which describes what ultimately happened. Okay.
This taking away is hidden in you.
Yes.
It contains the whole process.
To run this, you need some additional degree of freedom, which will take care of putting of sticking to the heat bath and taking away, and this system we do not consider here explicitly. So if you want to implement this, you need to have some additional degree of freedom that will take care of it.
What about the energy of this system, additional system which makes interaction?
Of this, so this additional system is like a clock. So it will not. You can implement this in such a way that the clock will not change its energy. And what's more important is that it shouldn't also change in entropy. So it shouldn't get mixed. So let me
Entropy of what?
More or less,
of the system.
Talking about is elastic collision.
Yes. Yeah. This is I think that. So while still you are working how to really implement it by means of explicit clock. And we have some results because it's even more important. It's even much harder to assure that it's after all pure state. It's not get mixed state because then we will be cheating. We will be drawing, say, for example, work at the expense of entropy of some other system, a clock. So that's some work in progress. So for a while we just are very simplistic and we simply say that this somehow can be done without cheating, meaning without taking energy from a clock and without polluting clock. So we here do not have clock explicitly and assume it will work. And this is equivalent. So as I say, so here is what I say. This is this Hamilton of interaction, and we assume that like initial and final states satisfy this. So it's like this collision.
Exactly the S matrix theory.
Yes, exactly.
It's called the S matrix.
Exactly. Yes. Exactly. Mm-hmm.
But without inelastic channels. Without inelastic channels.
Yeah.
Otherwise, this
Yeah. Yes. Yes.
permutation relation would not hold.
Yeah.
So
Okay.
S matrix.
Yeah. And this also puts some limitations to the whole our whole paradigm because if you want to have cyclic machines, then you cannot be really separate so well your system from a heat bath. So, but this we still have to work on. And
If this is mathematically equivalent to S matrix theory, how can you get any thermodynamics out of it?
the thermodynamics is put by hand because I say that the heat bath is in a Gibbs state. So this is where I put thermodynamics.
So you apply S matrix to a mixed state. It's still the S matrix theory.
Yes, of course. Yes. So it's maybe some details which normally you maybe would not think of, but now we just consider it in more detail. That one system is a Gibbs state, and the other system is some perhaps non-Gibbs state, and we apply and we consider this S matrix theory, and we look what we can get. Yeah, I think that's fair summary. And for example, our question is what states, from what state of a system I can go to some other state. We'll define work, derive optimal work extraction, and we'll relate to Landauer principle. Roughly what we obtained was that we have at least two free energies. So normally the amount of work that you can draw should be equal to change of the free energy. But here we have irreversibility. We obtained that you can draw less work that you have to put, and the work you can draw is one free energy change, and the work you have to put to create the system is different.
Used here in a normal sense or in a
So it's like standard free energy, E minus is exactly.
I don't understand what it means.
Later details, yes. So normally, so when I say free energy, I mean E minus Ts. E minus Ts. And I say in this paradigm you get the two different free energies that asymptotically give the old one. But I will tell you which are these ones. Okay? So we have used this. So this what you can do with this global unitary is we call thermal operations. So that's the class of operations, and then we have provided here formulas. When you can go from one state to other state by thermal operations. And also we defined
what is the meaning of thermal operations
it's
in the framework of S-matrix theory?
Yeah, it's simply you look only to the system, so you trace out the heat buff. So you have a system, and a heat buff. You apply this S matrix U, and then you trace out the heat buff, and you look what happened to your system. And this is some completely positive map. This is some operation on the system, and that's thermal operations. So
this could also be applied, the whole framework, to the case when you have two particles scattering.
Exactly, but then because here we get a lot of simplifications because one is a huge and Gibbs. So then we have nice answers, because if you have general collision theory, then everything can happen depending on what's the state of these colliding objects. So this provides some nice simplifications, and therefore we have final nice formulas. And we can call it thermodynamics, because at least one of the systems is somehow is thermal.
What is the assumption that it's weak?
It will need it. So in order to realize all transformations, we'll need the big. With small heat buff, you couldn't realize some transitions. Okay, and what I think is nice is that the definition of work is in terms of state change. It's maybe not very new.
That's precisely how the work is defined.
Will do.
In the book of Rife, in the Berkeley course of physics.
It's simply that
precisely that definition which is there. So
yeah, I joke. Exactly. I mean, okay. What will be new is that it's, I guess, it's deterministic, because normally it's macroscopic.
No, it's not macroscopic in the Rife book. It's precisely what.
Okay, maybe yeah. Good. It's very hard to discover anything, so I should look at that.
The definition
I should look at that. Yes.
What is highlighted here is not really a definition yet.
Yeah.
No, not yet. I simply say that we'll define in terms of state change. That's just this.
How it's
Yeah, in a while I will come.
But should we apply the quantum mechanical understanding here, or just classical?
It will be.
When you say deterministic and things like that, that is not in accordance with quantum theory, where we have only probabilities.
Yeah.
Theory, we have only probabilities.
Yes, but I want to have probability 1 in this case. So it's like.
What is the meaning of deterministic here?
I will have definition in a while later, because I condition arbitrary state to state transition, and later I will consider work. So let's first I will talk about the transition. So we have a result, which is that, well, and finally again it's easy combination of known results before. So it's very hard to discover anything new, but. So we have a theorem that if you can go from rho to sigma by this class of operations, if and only if, and now you have some scalar functions that you compare. So simply I will define in the next slide some functions of that for each state you simply define some functions on real functions, and you simply compare them. So no. This is to state is not you ascribe not a number, but a function. So each state gives you a function, a different function from state to state. So what are the functions? How it looks like. Sorry, will I have some definition of the function? Yes, I will have. So how it will look like. So to each state, so here you have the function will be from the domain is from 0 to z, so to partition function, and of the system. And values are from 0 to 1. And these are examples of these functions. For a thermal state of a system, the function is just a line. For other states, for the the results are only for states diagonal in energy basis. If they are not diagonal, then it's more difficult. So for states diagonal, so the theorem is, look, the theorem, it's like physicists who do not say, state the assumptions in the theorem. So mathematicians say theorem is assumptions and then thesis, and physicists' theorem is no assumption. so the assumption is that they are diagonal in Hamiltonian basis. And now we, so for other states than Gibbs, then they are simply such partially linear functions. And the result is this, that if the function is entirely above other function, then you can go from a state to state. So for example, from state sigma to eta, you can go because this function associated with sigma is entirely above the function associated to eta. But you cannot go from rho to sigma because, and the other way around, because these functions are not comparable. Neither is above the other one. And for...
Now, how do you know which function to choose?
I will define them in the next slide. So...
inverse Polish notation.
Yes. Yeah. Yes, exactly. Yeah, maybe I should completely rearrange this talk. So, yes. So now how I define the functions. So here is how we define. How we for any state, how we ascribe a function. So first of all, this state has probability. So it says it's diagonal energy basis. So it has probability of energy and some degeneracy. Sorry, that's the degeneracy of the eigenvalues, and that's the probability. Which, but sorry, G was the degeneracy. Yes, of rho.
By the way, this matrix theory is only applicable to systems with continuous spectrum.
Yeah. Yes. So heat buff.
You don't have the S matrix. You have the
yes. So this is a poor man description of. Well, no. The heat buff will be finally the heat buff can be here continuous, although we didn't yet fully worked out it. So we work in a poor man S matrix theory where we just assume that U commutes with these self-Hamiltonians, some of the self-Hamiltonians.
Then you don't have the S matrix.
No, we can.
S matrix was not U. But that was not S matrix.
No, this U was, yeah. No, I always consider it like a collision theory, and I always knew that yes, we lack. For example, we have our heat buff is finite dimensional systems, and then we prove everything with this. But what we should do, we should have continuous spectrum, and we should do this work. And for years, people tell us that we should do that, and it's hard, so we need some help. But the results are so nice that they have to carry over these. So we take these eigenvalues and we scale by Gibbs factor, and after rescaling, we order them. Then the function is a linear interpolation of the following points. So on x-axis, we simply put sums of Gibbs factors.
This beta is the beta
One of
which appears in the definition of the canonical system.
Yes. Yeah.
So this is the information about the real heat, but how that has anything to do with your small system?
Because
it's not in equilibrium.
Exactly, it's a good question. Because I have a heat buff in a temperature, and I allow arbitrary unitary that couple the system and the heat buff, and therefore these parameters, when I optimize over unitaries, this parameter it's finally I have it in formulas for optimal transitions between states of a system. So it's.
That don't mean that your small state eventually ends up in the thermal state.
It may. It may.
Oh.
But even if not, if I have initial state and final state, I may ask, is this? I may ask. No, I can go. I take arbitrary initial and final state, and I ask, is it possible? And of course, whether it's possible or not depends on beta. Depends on beta.
Beta is some parameter of the class of this heat bus.
Yeah.
Enters definitely the
must enter the formulas for the system because my system interacts with the heat buff. So of course it depends on heat buff. So on y-axis I put sums of Gibbs factors until z. Z is sum of all Gibbs factors, partition function. Then on y-axis I put sums of these probabilities. So this in this order. So I take this order, I take this probability, put here. Then I take these two, put here. So and that's how it looks like. So here you have this Gibbs factor. Then you have sum of them, and then you have z, which is sum of all of them, and then you have these probabilities, and they sum up to 1. And then, therefore, functions linear interpolation of these points. So that's the function. And as you see, clearly this function for Gibbs state is a straight line, because here you have everywhere equality, because that's simply Gibbs here, so it's just cancelled.
Enters in this way that you count on 1.
Yeah, but that's very simple to explain physically. This is a plot comparing a probability of state of this additional system, which is having energy E sub I, compared to what would happen if that system was in equilibrium with this giant in front of the other.
Yes, and
that's the very simple physical.
Exactly, and the thing is that I order it, so it gives me some order. This comparison gives me some order, and I use this order to define the function. Okay.
What is the degeneracy? Because
this degeneracy in the system, it simply gives me a longer straight line. So, for example, here, yeah, because these are equal. So. No, I really take them all, but yeah. Yeah, because it may depend on energy.
G is the degeneration
of a given. Yeah.
And there's other end of that. That's,
yes.
That's
GI. Yeah. Yes.
Yes.
Yeah. I. Good. So here is an example for two-level system. So my system is just two-level system, and then it's either it can be more excited than the Gibbs state or less excited. If it's more excited, if it's less excited, then it looks like more like this. So here you have smaller interval, and if it is more excited, then here you have smaller interval. If my system is an eigenstate of energy, then it's also effectively it's also straight line, because it's like this and here. So this you can think of it like also a straight line, because you may forget about this. So often it's helpful to think that it's just one line, even though it's actually such a function.
We know that physically with a two-level system, what's really distinguishable in this space is when there is a positive inversion. That's what is physically very important.
Yeah. So here,
for instance, requires this.
Yeah. So here, this inversion of population is not so here somewhere you get inversion of population if this will go like here. Yeah. But interestingly, here the most important is this being on each side of Gibbs state I am less excited or more excited. If I'm more excited, then I can then even have inverted population or not. It depends. So now so this is what I actually said. So if I look at the probability of excited state, then here's a Gibbs state, and more excited is like above, less excited is as here, and somewhere here is this where up here you have inversion of population, and down here you do not have.
Yeah.
Okay. And if both states are, if you want to go from some state that is like more excited to some state that is again more excited, it's easy. You simply have to admix some Gibbs state, and you go down. And with this class of operations, it's like the most easy thing. You can admix a bit of Gibbs state. And again, if you are less excited, you can admix a little bit of Gibbs state and go up. So it's easy to get some rule that I can that if I am on one side, I know from what state I can go to what state. And you can imagine that, of course, you cannot go back. What will be funny will be that you can jump over the Gibbs state. So you can change this class, which is funny because it's not doesn't satisfy detailed balance.
Very complicated formulation of a zero law of thermodynamics.
Yes, but we will get something more interesting by crossing.
The zero law of thermodynamics.
I think so.
I mean, the transitivity of being in equilibrium. That is precisely.
Maybe it's close to it.
System which is in equilibrium with the C system, and a B system which is in equilibrium with the C system, then A is with B. And that is how the normal temperature curve.
I'm not sure. Okay.
What means being cooling down or heating up?
Okay. Yes. So
this is
exactly.
Exact mathematical.
That's why what I like more is that you can jump from here to there. That's more interesting.
Cooling or heating.
No, because if you
more like a negative temperature.
Yeah.
if you
That's.
if you, no, the thing is that if you cool the system, you need some.
But there is no equilibrium here.
If you cool,
There is no equilibrium.
Probabilities are not necessarily
yes. These are not states in equilibrium.
This has nothing
Yeah.
to do with zero law of thermodynamics because there is no equilibrium.
But this is about but this is about cooling.
State is in equilibrium.
But
with
he
the
gives the other
and
state.
he has an
the big
addition.
guy. No,
Yeah,
the big-
and he has an addition system, and he checks what happened when he puts it in contact with this. And if it is hotter, then it
It's-
equilibrates down, and if it's cooler, then it
Yep.
goes up. And that's precisely.
But what's more interesting is that you can jump, and that's not so easy. That's not so. This is exactly the interesting thing.
That there are in equilibrium. But Łukasz,
So-
what does it mean that this two-level system
That
is in
this-
equilibrium with
Some other
That this is here. So it being this is a state in equilibrium with heat buff.
the two-level system always
Yes. So that's in no. But we have no.
different from
No. But we have Hamiltonian.
general from the different
No,
from
Rafa,
betas.
but we have Hamiltonian. So now only this state is in equilibrium. And what you say, I agree that this thing is like it equilibrates. So you stick and it starts to equilibrate. So, but there is a funny transition allowed, which is this jump, which is not like this. And I think it's nice. So here are these jumps. So you can go from some states from here up to here. Of course, not much up. So you can go from usually. Of course, you cannot go from here to there because that's then you would get inversion of population. But there are some states, such states, and that's funny. Here I draw this state. So you go from this. This is a more excited state. This is a less excited state, and because this is above this, you can go from this to this. So it's from more to less. And also here is another example where you go from here to there. It's not detail balance. So if you take this map, it doesn't satisfy detail balance. So I liked it. And
So for each of these cases, you have a unitary operation that
on that realize this. Yeah.
you have a specific model.
Yes. Yeah. Yes. Constructed one. Okay. Now I come to work. So macroscopic work is when I simply raise some weight, right? So microscopic work would be and deterministic work would be when I go from some ground state to some excited state. So I go from pure state to pure state. So the idea was that we don't want to. So that would be some ideal work because. Which doesn't, because what's the whole, to me, like I have a childish approach to thermodynamics. What's wrong with energy in thermodynamics? It's wrong. What is wrong with this is that it's polluted with probabilities. So, and what's work? Well, work is some pure energy, which is not polluted with these probabilities. Of course, in microscopic work, we still have a lot of probabilities because we simply like go, say, forward, a little bit backward, forward, a little bit backward. But somehow our cars finally goes really one direction and do not fluctuate like this. So this means that ultimately this macroscopic, due to lower to large numbers, we get some concentration of these small changes. But in microscope,
Quantum system? Or
this is a quantum system. Yeah.
You have to apply a bypass.
yes.
But then you have to use probability to describe the probability.
But I require that from initial pure state I go to final pure state, which are eigenstates. So then I want, this will give me like probability 1. So I impose it. I say I don't like to have output states that are superpositions of different energy states. Just I want to have eigenstates. And I ask, you know, can I, from a given state, can I go from here to there? Okay. And then I say, so this is very, so this is like a battery that I will look at the battery and see how much work I got. And that's a very poor battery because it accepts only this amount of work. So if I want to draw some other amount of work, I have to bring in a new battery which has a different energy level. So people now mostly work with, indeed, again, with weight, but like quantum weight. But with this, it's very easy to work to get nice results. So I will stick to this picture. And then what questions we can ask? So first of all, we have some system, we have some heat bath, and we have this ground state. And the question is how much. And we want that the final state is excited. And the question is, what is the W? How large can this be? So how much work we can draw? How much deterministic work we can draw from state to rho?
So there are 3 systems.
Now it's 3, yes. There is also battery. Like 4, yes, 4 because there is this system that, yes. Right, so that's a maximum extractable work. Now you have minimal work needed to form a state. So you want to backward process. You have some heat bath. You have heat bath. You have excited state, and then you can think that you take either you have already here. I didn't draw it. This system in equilibrium state, or just you take some system from a heat bath. It's in the equilibrium state, and then you want to make it non-equilibrium by using your work, using your battery. And then again, the question is, what's the minimal work that is needed to create the state out of an equilibrium state? And then finally, you have more general questions, a question that includes those two, which is that you simply have original state, you have some work, and then you want to go to this particular final state, and you ask how much work I need, or maybe I will even get work. So that's simply minimal work needed to do this. Well, this minimal work can be also negative, meaning you get it. All right? And you see now that this is a state change. So this is, I go from some initial state, and I end up with some final state. So I can apply the rules that I told you, which are valid for arbitrary states. And that's what I liked here. So meaning work is not something that depends on a path, because all these paths I have hidden in the optimization, because I optimize over U, which is optimized over all paths already, all possible ways. So work is now not functional because it's already is optimized. So, and now this is the result that gives the minimal the answer to this general question. So I have fixed state rho and sigma, and I ask what is minimal work, and the answer is actually very nice. Namely, you take a function of this guy rho, you rescale it until it will be above the function of sigma. So normally, if you don't have work, if you don't have a battery, this transition is only possible if this function to begin with is above this. But if you have work, the work means that you effectively rescale this until it's above, and then you can run the transition. So this is how it looks like. So initially, you have two functions that are neither of them above one another. So you cannot go from rho to sigma, from sigma to rho. But now if you put some work, this is the rescaling. So you multiply with W, and you try to multiply with minimal W so that this rescaled function is above this green one. And then you can go from this red to green. And that's the general answer. So we can now ask what are the particular cases. So here are particular cases, meaning what I want to say here. Okay, let me say. It turns out that the work of extraction is a change of some free energy, some like what was not for a while, it's not the standard free energy, it's something that we called mean free energy, and work that you need to put is max free energy. And these are not, in general, these are not equal to each other, so you lose here more when you put, you cannot extract then back the whole work that you put. If you have many copies of your system in the same state, then you know there is some law of large numbers, and then it turns out that these both functions, they fmin and fmax, they asymptotically go to standard free energy of a system, which is so E minus Ts. You compute for a given state, E minus Ts, and this precisely this, and then they are asymptotically they're equal. So you have reversibility as in standard thermodynamics. Here you have irreversibility because you are very restrictive. You want exact work. You are not happy with some fluctuations. Good. And here is some essentially how you can so this, for example is that you go from raw to a Gibbs state. So you have to from raw to a Gibbs. Let me maybe formation is nicer. You go from a Gibbs state, add some work, and you want to get sigma. So that's a Gibbs state. This is sigma. So you simply rescale it until there, and this gives you and then you are above sigma. So you can go, and then you can interpret the geometrically. So what does it mean? What is this amount of work that I have that shrinks me this z until here? So you see, it depends only on this slope, this first slope, because this whole line has to be here. So it depends only on the first slope, which means that it depends only on one eigenvalue. The one that is largest, but not largest absolutely, but largest in this Gibbs rescale order. And therefore, it's some relative entropy, but which uses only one eigenvalue of one state and one eigenvalue of the other state. And this is indeed, in mathematics, there are such relative entropies. They are more like, there are some Rényi divergences, they're called like that.
Can you give an idea how do you prove this theorem?
This?
Yes.
So this we prove by just, sorry.
This application of this previous one.
Of the previous one. That's a very direct application because I know simply
So the crucial is to understanding why it should be above that.
Yes, yeah. If you know this, then you simply then you simply apply it because this is a state, this is another state, which is another system. So altogether it's a system, and you have to simply play with these functions and see when this function is above this. So this is very easy.
There is something more than just drawing these lines that goes into the proof, and something which is even model dependent about the interaction that you.
Unfortunately, the basic result that the one function should be above the other already includes optimization over all possible interactions. So therefore, and we know what is the over all possible u's, and we have constructed u, so you can see what is this u, but it's not, and then you can go and maybe maybe construct some Hamiltonian interactions that does it. We did some maybe toy model, but we were mostly happy with this unitary, that we know what's the unitary. I can give a flavor. What's the unitary that does it? So maybe on Blackboard at some point.
We have a question. I mean, if you restrict it fully to classical picture, like only because you have diagonal states, so you can think about probabilities. So if you replace unitaries with just stochastic operations which are reversible, so permutation only, I think, then would you get something meaningful, or?
I tell you, so for this diagonal state and energy basis, actually it's very classical. It's classical, but what the relevant class is Gibbs preserving class. So if you have, you say, bistochastic matrices, permutations.
The only reversible stochastic.
Yeah. So on the whole system, we do indeed permutation. So this unitary is some clever permutations of the levels.
So this is classical in the sense.
Yes, these results are classical.
So
yes.
So you could say everything here without saying anything.
Exactly. Yes. For only the last slides of the talk will be quantum. Here it can be everything entirely classical. The total unitary is some permutations. So Yeah, so I didn't indeed look at the details. No, in some toy examples we looked what are these permutations that permute levels of a system, of a heat buff, and of a battery that comes up to this thing. You can do that. You can see explicitly what you have to do.
One more question. Is there an interpretation of this area between, let's say, yellow and blue light here?
Here?
Yes.
At this area?
Yes.
Don't know. Mathematicians for sure know, but because it's some. This is some Lorentz curves. You know, there's a lot of mathematics behind which people. So there are some in Olkin books. You can perhaps find these things, and maybe I don't know. Maybe there is some interpretation, but not. No, we in particular in our application we didn't come up to something that would be an area of this.
Assuming this.
That's a nice question.
Is supposed to have something to do with the thermodynamics. Now we have a transition with the work.
Yes.
The first law of thermodynamics tell us there's also something which is called heat.
Yes. Also, that's a good question.
How is
Yep.
that?
So heat here. Yeah. Exactly.
Change of energy.
Exactly.
Or heat.
So in this approach, heat you have to derive by taking energy change and subtracting work. So this is the way we.
Yeah, but that's something
So that's we
I
interpret.
don't understand,
Yeah.
because the heat in the usual thermodynamics might be related to something, for example, like a friction.
Yeah. So
Which is clearly not unitary operation.
no,
The interaction here.
on a whole system it is. Yeah.
On the bigger system, the bigger you
Yeah.
have friction. You lose here, but you gain, there.
So let me apply it to Landauer principle.
How do I describe the friction applied to this small system by this U?
Okay, it comes up. Friction comes up from some interaction with the environment.
What kind of friction? So if you have some closed peak system, so it's clear that the friction is definitely this. What is the difference between? If you look at the single system, you describe something by the friction. Okay, so this
Yes.
loss of energy.
But of course, it's hard to apply friction to a system which has two levels.
Okay, it's something, some analog of friction. Yes, so Landauer principle. So what's Landauer principle? It is that if I have a bit and if it's say with half probability 0 and 1 and I want to make it really 0, then I need to dissipate kT log 2 of work. I have to spend this amount of work. But this is for a degenerate system, so where both levels have the same energy. So in this paradigm, you quickly get the answer, what if they are not? So I have a system with two levels, and I can ask how much how much work I need to spend to make it ground, for example, or to make it excited. So now there are many ways of erasure of the initial state. Sorry, not ground excited. I want to erase. So I start with the equilibrium state, and I want to erase, meaning to make it like to make it, for example, ground or excited. Good. So, and then we have, so it's a question of work of formation. So meaning of work that I have to put in order to go from Gibbs state, which is analog of this, where I don't know whether bit is 0 or 1. So for degenerate Hamiltonian, is the probability half. So Gibbs state of a degenerate Hamiltonian is just all probabilities equal, half-half. Well, if it is non-degenerate, if the Hamiltonian is